guys. Let's think about another aspect of um, protein biology that's really important from the point of view of enzymes. Right? So returning for a moment to my example that I started our whole little section out with here on thinking about enzymes, specifically that HIV protease example that I sort of began with to sort of set the context of why one might want to study enzymes, um, uh, both to understand how they work, just the basic aspects of biology, and for the practical applications of developing drugs. And remember, I pointed out that HIV protease is critical for chopping up the GAG and GAG-Pol polyprotein so HIV can do its thing, and it's therefore something of an Achilles heel for this virus if one can figure out how to shut this enzyme down. And here's this is the structure of HIV protease, right? And a lot of the studies of this enzyme and some of these inhibitors were spearheaded by our own Tom Meek when he worked in pharmaceutical industry. So if you want to know more about some of this, you could certainly have a conversation with him about it. And as a result of a work of a bunch of different people, a whole family of different inhibitors have been developed that will inhibit the HIV-1 protease, right? And help shut this molecule down and keep it from processing those GAG and GAG-Pol proteins and therefore begin to collapse an HIV-1 infection, right? So here's an interesting thing, right? So that's great, and enzyme inhibition, steady state kinetics play a central role in understanding how molecules like this interact with and impact the activity of important enzymes. And therefore, this is steady state kinetics, as we've been talking about, is so important in enzymology. But I want to sort of use this as a bridge to another topic, another idea here. So this is the structure of that the apostate of that HIV-1 protease. It's an aspartyl protease, right? You can see this, it's a dimer. They're the two active site residues right down here. People have also solved the structure in the presence of some of these inhibitors, right? And this is one of them. I can't remember which one this is, right? Right down there in the active site. There's the active site aspartyl peptides. And you can see that these inhibitors are very clearly going to be competitive inhibitors because it's right down there in the active site in the way of where the substrate polypeptide would go, shuts the enzyme down like a classic competitive inhibitor. But notice something else. If you look at this structure, right, and then you look at this structure, what's something that ought to just jump right out at you other than the fact that there's something in the active site? Think about it for a second. The structure of the enzyme changed, right? You see pretty clearly that these loops sort of folded in, right, and kind of collapsed down on top of the substrate protein, right? In some ways, this is analogous to the structure I had you guys look at before, the avid and biotin interaction. Binding of the substrate molecule resulted in a significant change in the structure of the enzyme in response to binding of the substrate. And this isn't just some weird, odd phenomenon of HIV-1 protease, right? This is a general phenomenon. Again, I shy away from saying all. The vast majority, probably all enzymes, do some variation of this. Here's another example. That enzyme that I keep coming back to, that enzyme that helps make glucose 6-phosphate, starts off this critical pathway, metabolic piece of metabolism that we're going to talk about here soon, hexokinase, or its cousin glucokinase, right? Looks something like this, right? Fairly simple fold, right? It's actually related to actin, right? Same basic fold. Couple of lobes here, and there's this cleft that you see right here in the middle of this protein. Kind of looks like a Pac-Man. Guess what happens when hexokinase binds its substrates, glucose and ATP? If you had to just take a guess. The Pac-Man closes down, right? It clamps down. There again is that structural change as this enzyme interacts with its substrate proteins and clamps down on them as part of the process of driving this chemical reaction, right? And again, this is a general phenomenon, right? Across virtually all the enzymes, right? That you go from, say, open to closed states, right? So another way to think about this, right, is to go back over here thinking about the response of an enzyme structure to its substrate, remember the goal of an enzyme is to get the substrate, right, into its transition state, right? That's the whole idea. The enzyme is going to bind that transition state. It binds the substrate too, right? But the thing it really is trying to do is stabilize that transition state, right? Which means the sum total of the binding energy and feature recognition that an enzyme is going to apply is really aimed at that transition state to really stabilize it as much as possible. So if you think about this in one way, the enzyme essentially is distorting the substrate from its ground state into its transition state, right? It's reorienting things, it's straining bonds, it's doing stuff that you know, the substrate really has a hard time doing on its own, but the enzyme is going to help it do it. It's applying itself to helping drive or bend or move the substrate into that transition state. Well, you can think about this another way, because based on what I just showed you, right? Not only is the substrate being modified by the enzyme, but the enzyme is being modified by the substrate, right? There's a conformational feedback between the substrate and the enzyme. The enzyme pushes the substrate into its transition state. You can also say that the substrate pulls the enzyme into its activated conformation, right? So the fundamental core idea here is that these two events, the way in which the substrate acts on the structure of the enzyme acts on the structure of the substrate, these two things are, of course, there's that word again, thermodynamically linked, right? They're inextricable, right? They influence one another, right? And just going back to that scheme that we've seen before, we can think about this from the point of view of a thermodynamic cycle. I've done this for you guys before, but I'm just going to put it in this sort of enzyme context. So we can think about having an enzyme, right, for example, that can transition between its ground state and that activates it, the closed Pac-Man, right, or the closed aspartate protease, or whatever else is necessary to recognize the substrate and or subsequently the transition state and get this chemistry to go. And we'll just give that the symbol E star, right? Okay, and so we can say we'll just give that an equilibrium constant. We'll call that K star, and we're presuming that our system here is at thermodynamic equilibrium. Well, we know the enzyme can bind substrate, right? And so again, we're going to assume this is at thermodynamic equilibrium. So we're going to say, well, we're going to say there's an equilibrium constant here. I'm just going to call it K sub A, form that Cayless complex. But the enzyme could also, in its, you can also conceptualize it binding to and having an equilibrium with the sort of activated form, that conformationally changed form that's optimized for getting this reaction to go, right? So it could bind to that guy too. And we'll just call that one K sub B. And we'll give this sort of, E star S. So those are both Michaelis complexes. But in one case, for E star, we're in the closed or activated conformation, the sort of transition state, optimizing or ready to get to the transition state, however you want to think about it, right? And we can say, well, these guys are in principle in equilibrium with each other, right? So on the bottom down here, we'll just call this K sub S for substrate bound. You're essentially looking at the conformational equilibrium between the ground state of the enzyme and its conformationally changed activated state when the substrate's bound to it. So essentially the transition of the enzyme structure in the Michaelis complex versus up here at the top, the K star is just the enzyme doing this on its own, right? So we know, based upon our discussions of thermodynamic boxes like this before, that we can presume if everything here is at equilibrium, we can say the free energy around the cycle has to equal 0, which once again means that any two half paths, right, have to be equal to each other. So we can write out quite simply then that we know K star times Kb has got to equal Ks times Ka, right? Oops. Sorry, I put this in the wrong place. Kb, right? Okay, and doing like we did before, we can rearrange that, because what this means is that Ks, right, the equilibrium constant for conformational change of the enzyme with the substrate bound, divided by, or reference to, the equilibrium constant for that same conformational change in the absence of the substrate, must be equal then to the ratio of the binding constant, Kb, for the substrate to that conformationally changed optimized state, divided by the equilibrium constant for binding the substrate to the ground state, right? So the meaning of this should be clear based on the times we've done this before. The extent to which the substrate then binds more tightly to the conformational change in the enzyme. That's, again, that's the whole idea, right? The enzyme is going to change conformation in response to binding the substrate. It's going to increase its affinity as it moves towards a conformation optimized for binding the substrate. The affinity is higher than it is, say, for just the straight enzyme in its ground state. The extent to which that affinity is higher has got to match, right, the extent to which, right, the presence of the substrate then impacts the conformational equilibrium of the enzyme. So another way to think about this is that the binding of the substrate, right, pulls the enzyme into its activated conformation in the same way that the activated conformation of the enzyme pulls the substrate into its transition state, right? These two things are interacting with each other thermodynamically, and they have to be balanced in the same way, right? Or the magnitude of the effect of the enzyme conformational change on the substrate has to, by virtue of this assumption of thermodynamic linkage, occur sort of to the same sort of magnitude, right? Okay.